screen, right?
Yeah.
Yeah.
Yeah. Okay, guys. So today we'll be covering the last chapter in COA, which is memory organization. And yeah, we'll be covering what types of memory cells are there, SRAM and DRAM, and the internal organization of memory chips. And we won't get much into the SRAM and DRAM internal organization or error detection. We'll jump right into memory hierarchy, cache memory organization, and virtual memory system design, right? So let's jump right into it. So yeah, memory is like all about like storing bits, and like it's all about ones and zeros. It's about binary digits, and we've come a long way from like using vacuum tube CRTs and all these other methods to where we are now, right? And yeah, there's this balancing act that we need to like always maintain between size, cost, and speed when it comes to memory, because generally what is more expensive has like greater performance, and like what is cheap has lower performance. So we need to keep a proper balance of all these three. So that is what this chapter is going to be about, right? So these are some basic concepts like about how the processor talks to the memory, right? So you have an address bus and you have a data bus. So there's a k-bit data bus that goes from the MAR to the memory, and if there's k bits in the address bus, let's say four, right? So that will be 2 power 4 addressable locations. So you might have seen this before as well. So, and this is completely different from the data bus, the n-bit data bus, which deals with the word length, right? So, a word is basically like the unit, single unit of the like every addressable location. You can store one word, right? So that word could be of any length. So in this case, it's n bits. So at each of the 2 k addressable locations, you will have one word each, and the size of that word will be n bits, right? So you also have control lines between the processor and the memory that can be for read write or for memory function complete. Memory function complete is to send back to the memory to tell the processor that I'm done and you can proceed. So yeah, that is about like how the memory and the processor connect. So these are some like important terminology that we need to get into. So memory access time is the time between the read and the MFC signal that we were talking about. So it is between the read and between the function being completed. Whereas memory cycle time is the time delay between the initiation of two successive memory operations. So you'll know that memory cycle time will be slightly higher than memory access time, because memory access time is between the read and the MFC, whereas this is between like two successive memory operations, right? And then another terminology that's important is RAM, random access memory. Any location can be accessed for a read or write operation in the same fixed amount of time, right? So that is the crux of RAM, which is that that's why it's called random access, right? So you can like randomly access any location and it will still have the same amount of time to perform that operation, right? So yeah. Uh, So semiconductor memories are available in like a wide range of speeds, and their cycle times can range from like 100 nanoseconds to less than 10 nanoseconds. And obviously, the speed of the processor depends on the speed of the memory. So you can see that the latency and like the this time this to minimize all these latencies and these times is like very important, because the processor's efficiency also depends on the speed of the memory itself, right? So this is the internal organization of a particular memory cell. So we were talking about before about the address lines, right? The k-bit address lines and the n-bit data bus, right? So if you look into the memory cells over here, you have four address lines, right? Here k is equal to 4. So you have four address lines over here, and you have an address decoder. So this address decoder will take these address lines, and it will give you which word you need to access, right? So if you look at an example over here, if you have four address lines, and you'll have 16 word signals, right? Because 2 to the power 4 is 16. So this could be 0000, and that would be indicating the zeroth word, right? So similarly, if this was 000 and 1, it would be the first word. So yeah, every combination of this will have a corresponding word to it. So that's what the address decoder does, is like map a particular combination, the address of from the address lines to the particular word, right? And if you can see each of these words, so because they have four address lines, you have 2 to the power 4 words. So you have word 0 to word 15, as you can see. So those are the rows, are the words that you can find. And each of the columns will be corresponding to the data lines that we were talking about, the n-bit data bus, right? So each word will have over here the data line. You have seven, so you have eight data lines. So the size, that is the word size, is eight because you have from 0 to 7. So that's what this diagram is trying to show. And you have sense right circuits over here that are connected to each of the words, right? And you have over here, you can see B7 and B complement 7. So this is basically just like a optimization that's like not that much of an important detail, but like while drawing the diagram, you may want to remember it. It's an optimization that will help to like pick up the signal easier for the sense right circuit, right? Uh, so for example, if B7 over here is like 1, B dash 7 will be like 0. So instead of checking the exact signal length, the circuit will just check like which side the signal is coming from, here or here, and according to that, it will like figure out like you know whether this is 1 or 0. So that's just a small optimization that's done. So yeah, that is the internal organization of the memory cells. So moving on to chips with like if you have like a chip with 1024 bits, right? It can be planned as a 128 into 8 memory. So what this simply means is like you'll have 128 rows and 8 columns in this circuit, right? So 128 words and 8 columns. That is, each word will have a size of 8. So that's what this means. And the total address lines required will be uh, will be found like this, right? Since we need 128 rows, so we know that we'll need 2 par, so n will be the number of address lines, right? So if you have 2 par n, if you have n address lines, you will have 2 par n of these rows or these words. So the way you find n, or the number of address lines, is you just write the number of rows or the number of words, and then you equate that to 2 par n, and then you solve for n like this, and then you get the number of address lines over here, right? So that's how you find the number of address lines. And over here you can see that 128 into 8 bits uh, is like similar to 16 into 8 bits that we were looking at previously, right? So that's how this is found out, right? So you could arrange a 1024-bit memory like this with 128 into 8, or you could go ahead and arrange it like this, like into 1024 into 1, right? Which would mean like you would have 1024 rows or 1024 words, and the length of each of these words would just be 1 bit, right? So each of them would be just 1 bit each. So that is a different way to organize it. But as you can see, like it would be like a very long column, and it may not be the most efficient way. So this is like a somewhat better organization of that, same 1024 bits, which is like made into this array. This 32 by 32 memory cell array is formed with the same 1024 bits. And then you have you manage to like access all of this within a 10 address 10 10 bit address. So what you do is you take the first 5 bit of the address, and then you put it into the decoder, and then you will get 2 to the power 5, right? So you will be able to find like 32 words or 32 rows. So you're done with the 32 rows, but what about the 32 columns, right? So the rest of the 5 bits, you put it into this system, which has like a 32 to 1 output multiplexer and an input demultiplexer. So the multiplexer is like from many to one. So whenever you need the output, which is like when you have a 32-bit thing and you need a 1-bit output, you use an output multiplexer. And then conversely, you have the input demultiplexer over here, which goes into this same 32 by 32 memory cell array, and you get the output as required, right? You get the data input or output, which is 1 bit. So like you can either have the 1-bit input go in here, and then the demultiplexer will turn that 1-bit input into like a 32-bit thing, and then that will go into the memory cell. Or you could have a output of, or you could require an output. So here you will have from the 32-bit cell, you will have the output multiplexer output of 1 bit. So that's how this whole system works, and this is much more compact than using 1024 different words over here, right? So yeah, that is how we are optimizing over here with this 32 by 32 memory array, right? So moving on to the concept of static memory. So static just means that something retains its state as long as the power is applied. So the data will be erased immediately after the power is turned off, right? So this is not like permanent. The data is not permanently stored, and as soon as the power is turned off, the cells are erased. So you have static RAM, which is like fast and as well as it is expensive, right? So we won't go much into details of like how static RAM like looks like. You can look into like exactly how it works, but that is not very important. You can look into the cells and stuff, and you can CMOS as well is something we'll not be looking into deeply. Another thing that we will look at is DRAM, which is like less expensive than static RAM. It has simpler cells and higher density, and it has much more like bits per chip. So the density is higher and it's less expensive. But the thing is that they do not retain their state and they must be refreshed periodically, right? So if you recall, the SRAM is like faster, right, than DRAM. So if you require like a faster speed, you will use an SRAM. Whereas if you require a slower speed, you will use a DRAM. But if you require like more cost efficiency, you will be using a DRAM. Whereas if you are okay with a more expensive setup, you will use an SRAM, right? And also another thing that needs to be noted is that SRAM does not need to be refreshed, whereas DRAM needs to be refreshed like every 64 milliseconds. If you do not refresh DRAM, they do not retain their state, right? So those are like the main three differences. And again, we won't be looking much into the internal organization of DRAM, right? Okay, so moving on to like latency and bandwidth, right? So the speed and efficiency of data transfers among memory, processor, and disk have a large impact on the performance of a computer system, right? So it's both the speed and the efficiency that have an impact. And you have two things to take into consideration. One is the memory latency, which is the amount of time it takes to transfer one word of data to and from the memory. And then you have memory bandwidth, which is the number of bits or bytes that can be transferred in 1 second. So these are like related. So latency is the time for one word, and the bandwidth is like within 1 second, how much data, how many number of bits or bytes are you going to be able to transfer, right? So the bandwidth is not solely determined by the memory, it is also the product of the rate at which the data is transferred and the width of the data bus. So this is probably like a formula that you may need to remember, which is that the bandwidth is like a product of the rate at which data is transferred. So the data transfer rate and the width of the data bus. So those two things, right? So we will not be looking into this. But yeah, so moving on to larger memories using multiple chips, right? So so we can basically use multiple chips to like get larger memories, right? So if you look at this chip, it's a 512K into 8 memory chip. And let's say you want to organize this module, right? Or 2M into 32 memory module using these chips of this size. So how would you do that? Right? So it's a basic thing, right? Like 2M into 32 is basically M will be 2 power 20. So 2 into 2 power 10 into 2 power 10 into 32. So this is the required memory module, right? That's just converted from 2M to this. So this is a required thing, and this is the size of the chip that we have. So the number of chips that we require would just be like a division of like the total thing that we require divided by the amount that is there in one chip. So that will give you the number of chips that's required. So if you actually work out the calculation over here, it will actually come out to be 16 numbers, not 8 over here, which is what you can see over here as well. So this is how that is organized. So you can see there's multiple chips of 512 into 8 that are placed over here, right? So you have a 21-bit address, right? So here they have a 19-bit internal chip address. So if you can see, each of the chips is 512K, right? So that 512K will be worked out to 2 power 19. So for each of the internal memory address, you can see that it will require 19 bits, right? So that is why 19 bits are assigned for internal chip address. So within each of the chip, if you want to find the address, that is why we'll be using the first 19 bits, right? And these other bits, the 20th and the 21st bit, these A19 and A20, these two bits are fed into a decoder, right? And then you get 2 to the power 2, which is 4, so you get like the row which you need to find out, right? So this decoder will basically give you the row or like the location for which chip you need to access, right? So these first 19 will give you like the internal chip, and these two will give you which chip you need to access, right? So you just go into the row, and since you need to like implement a 2M into 32, right? Because it's 32 and this has only 8. So you will basically look at the entire row, and that will account for the 32, right? So here you can see 8 plus 8 plus 8 plus 8 will be 32. So these two bits will give you which row, and then you look at the entire row or the entire word, and the first 19 will basically give you the address, like which is internal to the chips, right? So that is how you use larger memories using these using multiple chips, right? So now the assembly of several memory chips on a separate small board that plugs vertically into a single socket of the motherboard are called as memory modules, right? So basically, instead of like permanently soldering the chip into the motherboard, we can make these modules which can be plugged vertically, right? In on a separate PCB, like it can be plugged vertically, and there can be two different types of these, which can be single inline memory modules or it can be dual inline memory modules. So single inline memory modules are sort of outdated and they will offer like only 32-bit, and this is the older standard, whereas the dual inline memory module is the newer standard with 60 to 64-bit data bus. This happens because the chip, both sides of the chip can have like different can carry different signals in this DIMMs, whereas in this both will have to carry the same one. So that is why this is called dual, and that is the current standard, right? So moving on to memory system consideration, right? So as we were talking before, the cost and the cost and the speed need to be balanced, right? The choice of a RAM chip for a given application will depend on like several factors, including the cost, the speed, the power dissipation, and the size of the chips. So now static RAMs are generally used only when fast operation is required mostly. So if you can think of where this is required, the fast operation is it's required like in the cache, right? The cache is like it's supposed to be like the fastest, and that is why we will be using static RAMs there. And in the main memories, which can like afford to be a little slower, we'll be using the DRAMs. And as we know, the main memory will have like a bigger size, so the cost becomes more important to like manage in the main memory, and that is why we'll be using DRAMs in the main memory. So that is something important to be noted. So moving on to the memory controller, right? So between the processor and the memory, we have a memory controller which can like provide a fresh refresh. So as you know that the DRAM which we'll be using will require a refresh every 64 milliseconds as we were talking about before. And that comes at a cost of zero point 0.2 milliseconds. That is like every time, every 64 milliseconds, you will do a refresh, and that refresh will take this much time. It will take zero point 0.2 milliseconds, and that is not that much of an overhead. It's less than 0.4%, right? So to do that, we will require memory controller. And other than that, a memory controller is required for communication between the processor and a memory and the memory. Because as you can see over here, the processor will give the memory controller its address, the read write command, and the request for the to start the clock cycle and the clock, right? Whereas over here, if you look at the memory controller to the memory, you will get the row column address, right? This address will be given as well as these two. So basically what it does is that it only like it separates this address into the row address and the column address, right? To keep it shorter. So it doesn't give both of them at the same time. And it only passes either the row address or the column address to manage the width of this line, right, to make it smaller, and to know whether or not this address is a row address being passed or a column address being passed, we need this thing, right, this strobe. It's called row address strobe or column address strobe, which basically, if this is, it's like a latch. If this is 1, that means the address being passed over here is a row address, whereas if this is 1, that means the address being passed over here is a column address, right? So that's how this works. And then you get the read write request that's passed on, and the chip select and the clock as well. And the data is like, as you can see, going like directly from the processor to the memory to like avoid like latency, right? So that is about the memory controller. So going on to read only memory, right? So memory doesn't need to always be like about like writing. It can be possible that certain types of memory may not be, it might not be required for us, the user, to like write anything, right? So read-only memory will retain its contents when the power is off as well, right? So it is non-volatile, and it can like store like, maybe firmware that shouldn't be accidentally changed by anybody. So it could be permanent or semi-permanent, right? And so read-only memory are usually set at the time of manufacturing, right? They can either be 1 or they can be 0. So over here, if you can see, there's a connection over here, which if it's connected, it stores to a 0. It connects to the ground and it stores to a 0. If it's not connected, it stores a 1, right? Then over here you can see there's a transistor and there's a bit line and a word line. So if the transistor is activated, that like if you want to read a particular bit, like a bit line and a word, right? So if the transistor is activated, it will be able to read it, and it will be able to see whether this is connected or not. So if it's connected, again it stores to a 0, and if it's not, then it stores to a 1. And in read only memory, this cannot be changed, right? So then the other type of memory you have is programmable read only memory, in which you have the same setup essentially, but this is connected with a fuse, right? So the default, as you can see, it is connected and the default is 0. But there can be like an electric, it can be burnt, right? There can be a pulse that can be sent, and this fuse can be burnt, which will change it to a 1, right? As you can see, if it's connected, it's stored as 0, and if this is burnt off and it's disconnected, it'll become 1. Now, as you can imagine, once the fuse is burnt, it cannot just come back again, right? Magically. So, this programmable read-only memory, it can go from 0 to 1, but that 1 cannot be further erased, right? So, that is where we bring in erasable read-only memory, right? Where the transistor can have a charge put into it that causes it to remain permanently open, right? But it can be erased with ultraviolet light. Here we use basically UV light if we want to erase the ones and make them back into zeros, right? So that is erasable read-only memory. And then you have electrically erasable read-only memory, which can do this without UV light, right? So additionally, since if you use UV light, you're basically going to expose all the cells together. But if you do this, if you use electrically erasable ROM, Then you can select which cells you want to erase and be more selective about which memory you want to erase. So then you have flash memory, which is similar to EEPROM, where each cell, a single transistor has a trapped charge, right? So that trapped charge is why it's like a permanent thing. But like it can be, as in like it doesn't go off like on its own, but it can be removed, and this can be removed. Like the read can be done individually, but the write is done in blocks, right? So this is like a important distinction for the flash memory, which is that the read can be done like selectively, whereas the write will be done in blocks, right? Moving on, it has greater density and it has lower power consumption. It is smaller and it is cheaper, right? So it has most of the like most of the criteria. This has like a higher advantage, right? So it can be a substitute for disks, and it can go like way beyond like a gigabyte too, right? So it has a higher cost, but it is portable, right? So like to just like refresh about all the types you have seen so far, you have ROM, which will be written by the factories and it's not erasable, written only in the factories and it's not erasable. The PROM thing can be like written by the user, and it's again it can be like it can be changed from 0 to 1, but it's not erasable. Then you have EEPROM, in which it will be written by the user. It can be written by the user and it is erasable, but only the whole chip can be erasable at once using UV light. And the double EEPROM can be written by the user and it can be erasable, and it can be erasable selectively as well. And it's done electrically. Whereas, so the flash is different because it is written by the user and it is erasable, but it is written in blocks, right? It is read in individual cells, but it's written in blocks, and it can be erased electrically as well. And in all the other criteria, this like sort of like beats all the other ones in terms of density, power consumption, and being inexpensive. And it can be a substitute for discs as well, but the only downside is like it's a higher cost, but it has more portability, right? So moving on to the memory hierarchy, um, so it is used for like obtaining the highest possible access speed, right? So we know that we need to balance between like cost and speed, right? So if like we want fast memory, like because we have fast memory that's expensive, we want that to be like smaller, and we want the cheaper memory to be like larger. Even though it's lower, we want it to be larger, right? So to like basically balance all of them, we have this layered structure, and it goes in increasing order, like it goes in increasing order for size, as you can see. Like the primary cache is like the smallest, and like the speed is the highest and the cost is the highest, and it's within the processor. And then you move on to the secondary cache, the main memory, and the secondary memory, each of which we will see in further detail, right? So this is like some example of secondary memory, including magnetic disks and magnetic tapes, and how they interact with the I/O processor, and how the main memory interacts with the cache and the CPU, etc. Right? So yeah, moving on to the cache memory. So the main memory is still slow in comparison to the processor speed, right? So like the processor, the CPU will be like much faster than the main memory, and that may mean that it may be holding us back in certain scenarios, and that is where we use the cache memory, which is small and extremely fast, right? And it is within the processor. Right? It's typically 10 times faster than the main memory, right? So it will use SRAM rather than DRAM that we see in like main memory, right? And it works because of something called locality reference, right? So this is quite an important topic where we basically exploit like some like important property of like the way things are arranged, which is like programs tend to spend their time focused on particular groups of instructions, right? So when you have like for example a loop or like frequently called procedures, you will be like repeatedly using certain set of instructions, right? So it makes sense to put those set of instructions that you're using frequently in like the more expensive and smaller memory, but like closer to the processor, so it's like faster, right? So localized areas of programs executed repeatedly during some time period, right? So most of the program is not necessary, not necessarily accessed during some time period. So this locality reference can be divided into two things, which is like temporal locality and spatial locality, right? So temporal locality refers to the time aspect. The most recently executed instruction is most likely to repeat soon, right? Like if you have a loop variable and it is like read and written in every single iteration, it makes sense to put it in the cache, like since every access is going to be a hit, right? Like because if you first access it and move it to the cache, it will be referenced again soon, probably, right? The next type of locality is spatial locality, right? So instructions near an executed instruction are more likely to be executed soon. And also, when fetching an instruction from memory, you can just move its neighbors into the cache as well. So we'll be keeping in mind these like principles while we are thinking about how we design like a cache and everything like that. Right. So uh, yeah, this is like how a cache sits between a processor and the memory, and the blocks of memory are transferred to and from a cache, right? So the processor access instructions and the data in the cache if there is a hit. So every time like a processor wants to access like a frequently used thing, instead of looking at the memory, first what it does is it goes to the cache. Right. So, and if it does like find what it's looking for in the cache, it's called a hit. And if like it turns out that it's not present in the cache, then we can either like go and look in the memory, or we can try to replace some block from the cache, and we can bring in a new block from the memory to the cache, right? So a hit is when a block is present in the cache that we're looking for, and a miss if it is in the main memory and not in the cache, right? So that is a hit and a miss. So looking at the cache memory, if you consider a cache that's like consisting of like 128 blocks of like 16 words each, right? So a cache of 128 blocks and 16 words each. So the total will be 128 into 16 words. That is a total of 2048 words, right? So blocks are so basically a bunch of words are like present in each block. That's how a block is, just a bunch of words in the cache, right? So the block size in this case is 16 words, right? So there's 128 blocks, 16 words in each block, and the total number of words are just a multiplication of that, which is 2048 words, right? So if we consider that the main memory is addressable by a 16-bit address, what does that mean? So K is 16, so 2 power K will be 2 power 16, which will give us 64K words, right? So if there's a 16-bit address, that means there's 64K different addressable locations. And at each addressable location, you can store a word. So you have 64K words that can be stored, right? And if you can see that the block size has 16 words, right? So if you divide this by 16, you get 4K. So you get 4K blocks that can be stored. So 64K words can be stored within 4K blocks, right, in the memory. So that's how this works. And if the main memory blocks can be modeled in many ways in the cache, in many ways onto the cache, and the cache is like content accessible memory, right? So content accessible memory as opposed to like random content addressable memory as opposed to random access memory or any other type of memory is basically addressed through not through the location but via its content, right? So it the basically like when the processor looks for a piece of memory, it looks at the content and it compares the content with the content of the cache, and that's how it checks for the whether it's looking for the correct location. So that is why it's called content addressable memory, right? So if you look over here, yeah, this is just our uh, the blocks that we were talking about before. These are the so if the main memory has 64K words, right, and each block has 16 words, the main memory will have 4096 words, 4096 blocks. And similarly, if you do the same calculation, similarly, to find how many blocks are there in the cache, you will find the number of blocks in the cache, right? This is like keeping in mind that each block has 16 words. right? So this is how it looks like. This is how the blocks will look in the main memory and the cache, right? So these are the 4095 blocks in the main memory, and these are our 127 blocks in the cache. So our task is basically to like map these blocks to like each of the slots in the cache, and each of the blocks in the cache, which we will see how we'll do that. And as you can see, the tag is required over here so that we can know which block in the main memory is this block corresponding to, right? So we need tags for that. And that is why we'll be looking at something called mapping, right? So mapping is basically the determination of where in the cache the blocks of the main memory are to be placed, right? These are also, so blocks are also called cache lines. So that's another term for blocks. And mapping is basically determining where the block from the cache is going to be placed in the cache. Sorry, where the block from the main memory is going to be placed in the cache, right? That is what mapping does. The other component of cache management is replacement, which is determining when to replace a block in a cache, right? So, as you can see, not all the blocks will fit in the cache. And at some point, you will see that the block that you require is not present. So, at that point, you may require a replacement of the block. And that is when you will need like a replacement algorithm to determine how to replace, like how to choose which block to kick out and which block to like take in from the memory, right? And throughout this process, we need to ensure that there is coherency maintained, and we can assure that there's no problem that arises from like the cache version differing from the main memory version, right? So that is where we need to make sure, like when we write in the cache, how is that reflecting in the main memory? Like, so we will look at that as well, right? So looking at the first component, which is cache mapping, right? So you can see over here, this is the main memory, and you can see the yellow block is like mapped to the yellow block here in the cache. And then the blue block here is mapped to the blue block. So that is just address map, that is address mapping. And the specification of correspondence between the main memory blocks and the cache blocks can be done through these three ways, right? We'll be looking at these three ways. So first we'll look at associative mapping. So in associative mapping, we just like assign, we can have any block location in the cache can store any block in the memory. So this is the most flexible type of mapping where it doesn't matter like which like slot we are looking at. If it's empty and if we need a particular block, we can just take it and put it in, right? So it's the most flexible. So it doesn't, the slot, which slot we're looking at the cache doesn't matter. So if you have a block, any location in the any block location in the cache that is like empty, it can directly take in a block from the memory if required, right? So a mapping table is implemented in an associative memory, and this is very fast and very expensive. So it's associative. It's called associative because like the order doesn't matter, right? So mapping tables will store both address and the content of the memory word. So they have the address and the content of the memory word, the data, right? So this is some what it looks like. So the main memory address can be of 16 bits, right? In this example of associative mapping, it has a main memory of 16 bits. So the main memory is divided into our blocks, and the cache is divided into our blocks based on the block size that we have discussed before. And then we look at the word and the tag, right? So each block, as you can see over here, can be identified. Like if you have 127 blocks, right? So each of these blocks can be like identified with just this tag, right? So within so 2 part 12 is if I'm not wrong, it's 128. Just a minute. Okay. So hmm. Okay, so basically, whatever, uh, so the word field over here, so we know that the block size is 16, right? So we know that it is 2 power 4 is 16, and therefore we'll have four bits for identifying the word within a block, right? This part of the address will identify the word within the block. And since we have 16 words in each block, we'll require 4 bits for identifying the word. So the remaining 12 bits, right, is used for like basically identifying the tag or like which block it is, right? So, yeah. So, which block amongst these we are referring to can be identified with the tag, and which word within the tag we are identifying, within the block we are identifying, is done with this, the word, the 4 bits. So, we look at the block size, 16, and we say it's 2 power 4 words. And so, we need 4 bits to identify which word it is within internally within a block, and then the rest of the tag bits can be used to identify which block it is from the main method, right? So this is the maximum flexibility since there's no fixed mapping, and so it is it's easier for the mapping. But the cons are that it's expensive because for each of this we will require a comparator, and that will become computation. That will become the hardware will become expensive for that, right? So if you can look at the mapping over here, you will have the address and the data. It will, this is the example for the associative mapping, right? So, yeah. So, here in the main memory, you can see this entire key is present, right? This entire key is present, and the data is also present, and the cache location the cache location is present here, and you have the address key, and the data is also present. So that is how you map from like the address to the main memory, and the data is also like mapped directly to the cache, right? So that is what associative memory mapping does, and this can have any number of locations, and it will need the say like the number of comparators required will be like the number of items in the cache, right? So that is why it will become expensive. And you can see over here, the key is for like the address to store to check the address, and the data is the data stored in that particular memory address, right? So that is how associative mapping works, right? So you can see over here that in this main memory address, which is like 16 bits, the tag has 12 bits and the word is 4 bits. So it's basically, since this word is like 4, so it's I- over here, since the word is like the 12th word within a block of the cache is checked, right? So that is how it works. So that is how associative mapping works. The tag is used for like finding which block it is, and the word is to check internally within the block where the word is, right? So since over here the word is the 12th word, we will be looking at the 12th word within the block identified with the tag, right? So yeah, that is how associative mapping works. And as you can see, we had the problem with having a lot of comparators, and we can maybe try to solve it using something called direct mapping, right? Here, each memory block will have only one place to load in the cache. So the mapping table is made of RAM instead of CAM, like we discussed before. And the n-bit memory address will consist of two parts, which is the k-bit index field and the n minus k-bit field for the tag, right? So if you look over here for direct mapping, you can see over here the main memory is like if you can see there's like repeating colors which are like indicating over here that all the same colors will like map to the same slot in the cache, right? So if I were ever to look for block 0, I know that I will have to look at block 0 in the cache as well. And if I ever want to see block 128 of the main memory, I will know that it is mapped to the block 0 over here. So block 1 will be mapped to block 1, block 2 will be mapped to block 2, and so on till block 127, which is mapped to block 127. And then you again go around mapping block 128 to again the first block, right, to block 0. So you keep repeating that process. And essentially, that is how like you map like multiple blocks to this particular block, and you will never find block 0 in like a different block in the cache other than the one it's mapped to, right? So that is how direct mapping works. And if you look at the yeah, if you look at the address over here, the word address again is 4 bits, because again the block is of again 16 16 sorry words, right? There's 16 words in each block. So to find which word it is in the block, you need 4 bits. 2 power 4 will be 16, and you will find which word in the block you're looking for. And the rest of this, which you can think of as the index, is to find the tag and the block, right? So the tag will find you like for each of these 128 blocks, you will have a particular tag, right? And sort of and then there will be 7, right? So like you can see that there'll be block 0, block 120, and similarly there'll be like 7 such blocks mapped over here. So the way you will find that is basically you will first find the word field similarly, and then you will see that the number of cache blocks is 128. So 2 past 7 will be the block field, right? 2 past 7 is 128, and therefore it will be the block field, and the remaining will be the tag field, right? So first you find the word field based on the block size, right? Block size is 16, so you say 2 power 4 is 16. So the words bits will be 4. And then next you move on to the block field, where you see that there's 128 blocks in the cache. So you do 2 plus 7, and that will be your cache, the number of bits in your block. And then the tag will be the remaining one. So that is how direct mapping works. So if you can see over here, uh, yeah. So this, if you can see, is like the tag, and this is like the index, right? This will have like the word and the block part of this, and this is divided into this, and this is the tag part. So first you will have an address, and then you will compare this part, right, the block and the word part, with like what is there in the cache. And once you see that there is a match over here, you will see that there is a match. You will move on to like check whether the tag is like the same or not. So you will use a comparator over here, and you will check whether the tags are the same or not, and based on whether it's a match or not, you will see that it's a cache hit or a cache miss, right? So that is how direct mapping works. So, yeah. So this is again another example where you have a tag and a block and you have, this is the tag part of it, and this is the block part. And since it is this block part has 127 stored in it, so that means we need to look at the 127th block of the cache, right? So the block part which corresponds to the cache, as we were saying talking before, uh, we'll have to look at the 127th block of the cache. After we find the which block we're looking at the cache, we look at the word, which is over here in this case, it is 12. So we will look at the 12th word of the 127th block in the cache. So if all of these three are matching, we will say that we have got a cache hit, right? So this is again an example of like where you how you store the tag and the data as well in the cache memory, right? The corresponding data will be stored in the cache memory. Yeah, so you can see the tag and the index combined will give you the memory address, and the corresponding data is always stored together. So yeah, that is another example of direct mapping with a block example. And that is about direct mapping. So we've so far covered direct mapping, and we've seen associative mapping. So if you can think of what kind of problems you would face in direct mapping, uh, the first thing that we would think of is probably that since we are we're reserving this block for only these, so the first block, in this case, block 0, is reserved for the yellow blocks, as you can see. So there may be a case where we don't need a yellow block at all, and the cache is completely full, right? So in this case, it will be like useful for us to store like probably this red block in this first block in the cache, right? In the first slot of the cache. But since it's direct mapping, we're not allowed to do that. So it is possible that a lot of space can be wasted in the cache, right? It can like lead to like repeated misses as well, and so that could be a problem. So that is why to like sort of balance like and combine like the effects of like associative mapping and direct mapping, we have a different mapping called set associative mapping, which is a combination of both of these techniques, in which the blocks of the cache are grouped into sets, and the mapping allows a block of the main memory to reside in any block of a specific set. So basically, what happens is that uh, within each set, you have associative mapping, right? So they're grouped into sets, and within each block, you have associative mapping. But within each set, you have associative mapping. But to the sets, you have direct mapping, right? So, for example, in this case, you can see uh, that you have set 0, set 1, set 6, 63, etc. And like over here, you have two blocks per set, and you could have associative mapping within each set. Like if I were to place block 0 over here and block 1 over here, this block over here, I could like rearrange them internally within the set, and that wouldn't matter. That can be done. But I can never put block 0 in like another set other than set 1, for example, right? I cannot put it in block 3. So it is directly mapped to the sets, but internally within the sets, it has associative mapping, right? So that is set associative mapping. And again, you have over here a 16-bit memory address. The word field again is similar to the previous cases, is found to be 4 bits. And the sets set so the block is like 6 bits, and the tag is found to be 6 bits, right? So if you look at more examples over here, each block has a set of locations in the cache to load, and set associative mapping cache with a set. So this is set associative mapping cache with a set size of 2, right? So if you just look over here, this is your tag, and this is your index, right? So if you look at the index, and if you find a match over here, you will, as you can see over here, there's a match that's found, and you will look at the corresponding things in the cache that are matched to it, and you have to check with these two, right? There are two tags, and there's two datas over here and in the cache at the same index, and you basically take this address and you use two comparators over here, and you check with both of them, and you can find that in one case that there's a match, and in another case there's not. So since it's a two-way set associative, you can see that we needed two comparators. And if it was three-way set associative, you would see that you would need three comparators, and like so on, right? So yeah, this is like an example um, of the main memory address, which is 16 bits. You have the tag bit over here, and then you have a set bit, like you have some bits for the set. So that is basically the block, right? The set is nothing but the block. So it just says that you need to look at the 63rd set in the cache, right? The block always like tells us to like look at the cache, right? So whatever is in the block, it will tell us to like look at the cache. Since over here it is 63, it will tell us to look at the 63rd set of the cache, right? And then the word will help us identify which word it is within that set, right? So yeah, that is how set associative mapping works, right? So if you look at the mappings you've seen before, if you look at associative mapping and set associative mappings, there may be cases where we need to like replace or like kick out some blocks, right? You know that we won't have that in direct mapping, since like it is like we won't have, we will have replacement in direct mapping, but we won't have a problem in figuring out which to kick out, because you know that a certain block can only, a certain slot in the cache can be mapped only to a certain block in the only to certain blocks in the main memory. So you know that if a particular block is not found, or if there's a cache miss, you know that you have to like kick out that exact block which like is taking the place of that particular block that you're trying to find, right? But like in case of associative or set associative, we have to like find an algorithm to know which block to kick out, right? So that is where we'll have to look into some replacement algorithms like LRU, least recently used block. And here the cache controller will track the references to all the blocks as the computation proceeds. So you will have to, if you want to see which is the least recently used block, you have to have some way to keep track of it, right? You need to keep track of which was used least recently. So that is why you have a cache controller which tracks the references, and you have increase or clear track counters based on when you have a hit or a miss, right? So you have these algorithms like first in first out and least replacement, least recently used algorithms, which basically tries to find out which location should be emptied when the cache is full and the miss occurs, right? So how will we distinguish between an empty location and a full one? We'll use something called a valid bit, which will be like 1 if the location is full and 0 if it is empty, right? So we can use these two algorithms and keep track of like uh, keep track using our cache controller, and implement either of these algorithms, and make sure that replacement is done appropriately, right? So we were talking about cache coherence before, and that is why cache writing becomes like a topic we need to talk about, where cache writing can be done in two ways, right? If you want to like perform a write operation, you can either perform a write through or you can do a write back. So how write through works is that when you're writing into memory, if the cache, like if you have a hit in both the cache and the memory, then it's easy that then you just write it in parallel, right? So if there's a hit, you don't have much of a problem. You can just write, you can completely like write through, right? You can parallelly write through. But if you're performing write through and you find a miss, then what happens is that there's no writing in the cache, right? There's nothing to write in the cache because you didn't find the location in the cache. So what you do is like so if you have a read miss, for example, so the missing block may be overloaded onto a cache block, right? So if you have a miss in if you have a reading miss, then the missing block should be overloaded onto the cache block before you write it, right? So before you write, of course, you will like check whether it's there or not, and you will have a read. And when you have a read miss, you will first have to like overload the cache block with the missing block, and only then you can write. So if it's a hit, you can just write in parallel. Whereas if it's a miss, you basically have to first load it into the cache and then you have to write, right? So the memory is always updated when you use write through, because you're making sure that as soon as you write in the cache, you're writing in the memory as well. So that is like good and important if like the CPU and the DMA IO are both executing as well, right? So if the CPU is executing as well, it will require like the updated memory, right? So it makes sense that it will want the memory to be updated and write through operations need to be performed. But this, of course, will become slow because to update the memory will become much slower than updating the cache. So since we have to update the memory at each point, this will become slow, right? So at this point, you can use a write buffer too, which we will discuss later. So the other way to write is using write back. So when writing into memory, if there's a hit, then only a cache, only the so when you're writing back, we only write in the cache, and we basically like wait for that block to like return to the cache, right? So if there's a hit, only the cache is written, right? But what happens when there's a miss? So when there's a miss, the missing block is brought to the cache and then you write it into the cache. So far, it's the same as before. But instead of writing it into the memory, like before, we don't do that. So the candidate block, for a read miss, the candidate block must be written into the memory, right? So if there is a read miss, the candidate block must be written into the memory. That is like if in the future, like after you write in the cache, right? Like so far you only write in the cache, right? If there's a hit or there's a miss, you only write in the cache. So later on, you're performing an operation, and let's say there's a read miss. So which means you're like updating the cache, right? So if you kick out a block, if there's something written in the block and you've just kicked it out, then you need to make sure that since you're kicking it out, you need to update the memory, right? So that is when you update the memory over here when there's a read miss or when like it needs to be updated, right? So in this case, as you can see, that the memory is not always up to date, and like the same item in the cache and the memory will have different values before you write back into the memory. So this will be a problem in some cases. So you need to choose cache between cache write through and write back appropriately. So since we are writing in the cache block, we can mark it as dirty or modified. So to like ensure that you can see that this block has been modified. So whenever you're sending that block back to the main memory, you can just write it back, right? You need to update the memory, right? So copy it back into the main memory when another block needs the cache space, right? So that is how write back and write through will differ, right? So here are some performance considerations that we need to take into account, right? So there's two factors, performance and cost. So this ratio of like price per performance is something that we will need to look into. So we want the price to be lower and the performance to be higher, right? So we want to like minimize this ratio. So the performance, though, it depends on how fast the machine instructions can be brought to the processor for execution and how fast they can be executed, right? So if you bring the instructions from the if you can bring the instructions from the memory to the processor faster, that means the performance is increasing, but the price also increases, right? So that is the problem. And for memory hierarchy, it is beneficial if it transfers to and from the faster units can be done at a rate equal to that of a faster unit, right? So the rate of the transfers needs to be equal to the rate of the faster unit, right? So uh, if the like for example if the cache like if the for the memory hierarchy, like if the faster it is beneficial if the faster units like the cache are like closer and the transfers to and from the cache are faster as well, right? So that is why the cache is placed closer. So this is not possible if both the slow and the fast units are accessed in the same manner. However, however, it can be achieved when parallelism is used in the organizations of the slower units using interleaved organization, right? So interleaving is basically this. So if the main memory is structured as a collection of physically separate modules, right? So these are some physically separate modules that you can see in the main memory, and each of them will have its own address buffer register and its data buffer register. So the main memory is separated into these separate modules. So we just want to make sure that we can parallelly access them, right? So the memory access operations can proceed in one or more module at the same time. So, for example, if there's a memory request, if there's some memory operation happening over here, while that operation is still happening, we can proceed and we can do a operation over here as well, right, in the second module. So that will basically uh, like reduce the latency, and that is what we call interleaving, right? So over here you can see that the address in the module has m bits and the we have k bits to identify the module itself, right? So this is like the k bits for like so 2 per k will be n over here since we have n modules, and m bits for like within the internally within the module what is the address to find that. So that is about interleaving. So the hit rate and the miss penalty, right? So the success rate in accessing information at like various levels of memory hierarchy are called like hit rate or the miss rate, right? So ideally, the entire memory hierarchy, like in the ideal scenario, the entire memory hierarchy would appear to the processor as a single memory unit that has the access time of a cache on the processor chip and the size of the magnetic disk, and depends on the hit rate, right? So in the ideal scenario, we want like the access time of the processor like which is like the fastest, and we want the size of the magnetic disk, which is the slowest, sorry, which is the largest and the slowest. So we want like the largest and like the fastest in the ideal scenario. But since that's not possible, we'll have to find like a balance to like basically increase this hit rate, and like decrease the miss penalty, right? So a miss causes extra time needed to bring the desired information to the cache, right? So this is the formula that we'll need to remember for finding the average access time experienced by the processor. So the average access time, it'll depend on three things, right? It'll depend on the hit rate, how often you're like able to hit the like how often you're able to find a good hit, like a cache hit, and then you'll have the miss penalty. So every time you miss, right? Every time something is not in the cache, you need some time to like go back to the main memory and like collect it and like bring it back to the cache, right? So that is the miss penalty. So one minus the hit rate, right? So that is like basically the miss rate into the miss penalty, right? And C is the time to access information in the cache. So this is basically the rate at which you find something in the cache into like the time taken to get the information from the cache, plus the rate at which you miss into like the time that you will need to take if you miss, right? And that will be the average access time that is experienced by the processor. So how do we improve hit rate, right? So you can increase the cache size, right? You can make a larger cache, but that will of course come with an increased cost. You can also increase the block size while keeping the total cache size constant and hence the cost constant. But what happens if the block size is too large? So if the block size is too large, it may happen that some items may not be referenced before the block is replaced, and the miss penalty could increase. So you need to find the sweet spot between between having too large of a block size and too small. Because if you have it too large, then you can keep missing, right? Because you may bring in unnecessary number of bits, right? Because the block size, it's like you may need only a certain amount of uh, size for a certain amount of data within that block, right? So that is why we need an optimal block size. So yeah, moving on to the different types of caches on the processor chip, right? So you can have a cache on the processor chip, or you can have it like outside the processor chip. So when you have it on the processor chip, it's called an L1 cache. It is faster and smaller, and it can access more than one word simultaneously, and lets the processor use them one at a time. So L2 cache is like outside the processor and it is slower and larger, right? So these are the two levels of caches, right, that you can have, and these are on-chip or off-chip caches. Another thing that you can do is you can have separate caches for like instructions and data, right? So like what would happen if you have separate caches versus what would happen if you have a single cache for both instructions and data, right? So if you have just a single cache, you would have a higher hit rate. Because if you have a separate, you can imagine like and at a certain period of time, you don't really require many instructions and you require a lot of data. So the area that you've the memory that you've set aside for the instructions is going to waste because that is being empty and you only are using the memory that you allocated for the data, right? So in this certain period of time, since we only are using this cache, right, the data cache, and we're not using the instruction cache, which we could have just used. We could have just put more data in this if we had used a single cache, but now it's just sitting there empty, right? If we use two caches. So for getting a higher hit rate, perhaps a single cache would be more useful, right? But again, the problem is like when we want to you do like parallelism for like overall better performance, we may want separate caches, right? Since if you can think of it, it may be possible that in a certain time, you want like a certain instruction and like a certain data to be in the cache at the same time, right? But if you're using a single cache, the instruction may just the data may just be like evicted out, right? And if the data is evicted out but the instruction like depended on that data, then like you will have a problem there, right? So the parallelism of like the parallelism can be like preserved better, and like the performance is like achieved better if you have like a separate cache for both the instructions and data, so that you never have to like, if the instruction is like dependent on the data, you never have to worry that there's that is kicked out, because you always have like a certain space assigned for both of them, right? So yeah, that is about how you can divide like your caches for like instructions and data, and what are the levels of caches that we have. So if you've seen the average access time formula before, we were depending only on one cache. Now since we have L1 and L2 cache, we'll have to make a modification to our T average formula, which is basically just we'll be calculating for the first cache, and then again we'll be calculating for the second cache, and we'll just simplify that, and we will get this formula over here, right? So yeah. So there's some other enhancements that you can do. Like you can use a write buffer. That is, the processor doesn't need to wait for the memory write to be completed. So as we know that writing in the memory can like take more time, right? Like than writing in the cache. And like the processor like will need to wait. Like if there is a need for like writing in the memory, the processor will need to wait for that. But so instead of doing that, if we have a write buffer, the processor can just put its information in this buffer. It can write it in its buffer, and it can just leave, and it can do whatever other work it has to do. And the write buffer can like handle writing it into the memory, right? So the write buffer will go ahead and like wait, and it will write in the memory whenever it's possible. So the processor doesn't have to be engaged in this. The write buffer will take care of the waiting. So that is one enhancement. Another thing you can do is you can prefetch the data into the cache before they are needed. Again, this can be done like based on the hardware can predict which memory locations you'll need soon, and that can be done based on the locality of reference or any other method, and you can basically hide the missing latency, right? Then you have a lockup free cache, right? So the processor basically is like able to access the cache even while a miss is being serviced. So normally, if like a miss, if you encounter a cache miss, then you basically just freeze the cache, and the processor is not able to access the cache anymore, right? But you can do this, you can use a method where the processor can just continue issuing memory requests even after a miss is being serviced. So it's also called a non-blocking cache, where the cache just basically stays available for the processor even when a miss is being serviced, right? So that is called a lockup free cache, and these are some enhancements that can be done, right? So the performance of a cache. So all the memory accesses are first directed to the cache, right? Or specifically the L1 cache. And if there's a miss over there, you check in the L2 cache. And if there is a miss over, so if the word is in the cache, then you just access the cache provided to the CPU, right? But if there's a miss, and if the word is not in the cache, you need to bring that block, including the word, to replace the block into the cache, right? You need to bring it from the main memory to the cache. So that is like what you need to do to like uh, enhance the performance of the cache, right? So next we'll be looking at something called virtual memories. So the problem we'll be dealing with is that the physical main memory is not actually as large as the address space spanned by an address issued by the processor, right? So the actual main memory that we have, the physical main memory, is not as large as the address space spanned by the processor, like by the address issued by the processor, right? So the processor like basically requires more like more address points, or like more memory than what the physical main memory can offer. So when a program doesn't completely fit into the main memory, then parts of it are not currently being executed. The parts of it that are not executed are stored on secondary storage devices, right? So basically a program may not completely fit into the main memory, and the parts that are not being executed are stored in the secondary storage devices. So the techniques that automatically move the program and the data blocks into the physical main memory when they're required for execution are called virtual memory techniques, right? So virtual addresses will be translated into physical addresses. So yeah, the virtual memory organization looks something like this, where you can see over here that the addresses issued by the processors are the virtual addresses, and the memory management unit in between the processor and the cache will basically convert this virtual address into a physical address and give it to the cache, right? So these techniques are called virtual memory techniques, and the the address space is basically like expanded beyond the physical main memory into the secondary storage devices as well, right? So how does this address conversion or address translation, how is this done by the memory management unit, right? So all the programs and data are composed of fixed length units called pages, right? So each of the programs, they have units called pages, and each of these pages consist of blocks of words that occupy contiguous locations in the main memory. So the pages cannot be too small or large, and they have a contiguous block of words which are in the memory. And the virtual memory mechanism bridges the size and speed gaps between the main memory and the secondary storage. So if you can see over here, this is similar to like what the cache is doing for us previously, as we were seeing. It's sort of analogous to that, that the cache was basically trying to like bridge the size and the speed gaps between like the main memory, right? Like it was trying to help the main memory by bringing the things from the main memory to the cache when required. And similarly to that, the virtual memory will bring the data from the main memory, like from the uh, secondary storage to the main memory as required, right? Like it will do that in the like form of previously we were just thinking of blocks, and now blocks or lines, right? Word lines, and now we are going to be talking about pages. So this is like an example of like address translation, where you have a program one and you have like a virtual address space for the program one, and there is a translation map. And after and using this translation map, you can basically map the virtual address space into the actual physical address space. Similarly, you can do this for the other program as well, right? So over here you can see that we have a page table, and you can see that the there's the page register there's a page table register, right, which stores like the address for the page table itself, and like the virtual page numbers, right? So over here you will have like the indices will basically be the virtual page numbers, and what they will map to will be the actual physical addresses of the main memory, right? As you can see over here, they are mapping to the actual physical addresses, and the indices will be the virtual page numbers, right? And there's other valid bits and other flags like which can identify whether or not a particular page is present or not in the main memory, right? There's bits for that, right? So yeah, over here you can see how this address translation is exactly done. You get the virtual address from the processor along with a virtual page number and an offset, right? So you get a page table register over here with a page table address. So once you add the virtual page number to the page table address, you will get the page number in the index in the page table, right? So you can think of this like you don't know where in the memory the page table exactly is, and that is why you need the address, right? So you can just think of this as this is like the index within this, right? So if this was zero, right, like if this was stored page table address was zero, then you would just directly use this virtual page number, and that would directly be the index. But since the page table is not going to be stored at zero and instead going to be stored at some other place in the memory, so you just add whatever that address of the page table is, so that you can get the index over here to be the virtual page number required. And if you add that, and if you like see the corresponding thing that it's mapping to, it will give you the page frame or like the physical address in the main memory, right? And then the offset is the same. The offset is basically the internal offset, like within the page, which word or which bit are we talking about. So that offset is just directly the same for like even after the translation. The only thing that's changing is that the virtual page number is being looked up in the page table, and it's the corresponding physical address is being given to us, right? So the page table information is used by the MMU for every access. So it is supposed to be with the MMU. However, since the MMU is on the processor chip and the table is rather large, only a small portion of it, which controls the page table entries that correspond to the most recently accessed pages, can be accommodated within the MMU. So we're basically looking at the fact that the MMU is on the processor chip. So that means we can't have the entire page table to be stored in the MMU because the page table is very large. And if we store the entire page table in the MMU, which is in the processor chip, it will become difficult because it will entirely be stored in the processor chip, which is not possible. So what we want to do is we want to it is impossible since it's impossible to include the complete page table in the processor chip. We only take a portion of it, right? And this portion it consists of the page table entries that correspond to the most recently accessed pages. So again, if you see, it's analogous to like how we use the algorithm, the least recently used algorithm, to like kick out the blocks we were using previously in the cache. And like we wanted to maintain the most recently used ones, right? So similar to that, over here, the TLB wants to like retain the most recently accessed pages, right? So, like a small cache called the translation look aside buffer is incorporated into the MMU for this. So, it is just a small cache and it's called the TLP, right? So, if you look at this diagram over here, the virtual address from the processor is is like put in over here, and we check it with the virtual page number, right? So we take the virtual page number and we find in the table. We check with each and every one of these indices, as you can see in the entire table that is over here, which will not be the entire page table. It will be the entire TLB, right? It will be the entire translation look aside buffer. We check with each of the indices and we see if there's a match, right, over here. So if there's no match over here, it's a miss. And if there is a match,